Good day and welcome everyone to the Dotz Nano Investor Briefing. Before I turn the call over to Sharon Malka, the CEO of Dotz Nano, I'd like to remind everyone that during the event, speakers may make forward-looking statements. Forward-looking statements are subject to numerous risks and uncertainties as described in the company's annual report and within other filings. And I'd like to reiterate that this is being recorded. I would now like to hand over to Mr. Malka.
Thank you, John. Welcome everyone to our investor briefing, which will feature a presentation by industry experts who will provide an overview of the carbon capture landscape, recent industry trends, and carbon capture technologies. We will also provide an update regarding the development plan of Dotz Earth, our innovative carbon capture technology, the progress we made, and our future plans. We are very excited about the opportunity for Dotz Earth, and hopefully at the end of this event, you will share our enthusiasm. I would like to begin with a quick overview of our company. Dotz is an Australian developer of innovative climate and industrial nanotechnologies with R&D based in Israel. Our primary focus is around groundbreaking carbon management technologies. Led by experienced leadership team, our intention is to leverage our nanotechnology portfolio, targeting a multi-billion market opportunity. Dotz was founded in 2015 by Dr. Michael Stein and Professor James Tour from Rice University in Houston, Texas, USA, to commercialize carbon and graphene quantum dots technologies. Since establishment, Dotz identified market opportunities that align with the company growth strategy and vision, which is harnessing nanotechnologies and advanced material to tackle global, environmental, and industrial challenges. In the last few years, we have developed and commercialized our industrial tagging solution, where we currently in discussions with leading customers to secure commercial collaboration, mostly in the energy and chemical sectors. Earlier this year, the company completed a strategic acquisition of an innovative CO2 capture technology, which we call Dotz Earth. Dotz Earth, which was initially developed at Rice University, represents the next evolution in carbon capture technologies as it aims to address the key challenges associated with the current technologies and offers enhanced efficiency and sustainability in rapidly growing carbon capture market. We now focus our attention on developing carbon management technologies as enablers of reducing carbon emissions. And our intention is to position ourselves as a technology developer and provider of carbon management technologies. Before I turn the call over to Glenn Kelly for the first presentation, let me first quickly provide an overview of our agenda for this day. We will begin with a presentation from Glenn Kelly, an expert in the climate technology sector and soon to become our board member, who will discuss the carbon capture landscape. Yasmina Kafka, research manager at SINTEF, one of the leading global research organizations for climate technologies, will follow with an overview of carbon capture technologies. Professor Tour from Rice University, Houston, Texas, will describe the innovative process of converting plastic waste into a carbon-based solid sorbent. And finally, Michael Stein, Dotz co-founder and CTO, will discuss the Dotz Earth development plan. Following the presentations, we will have a Q&A panel where the speakers will address questions received during this event. Thereafter, I will provide a company update and discuss the future direction of the company. We have a busy event indeed, so without further delay, let me introduce our first speaker, Mr. Glenn Kelly. Glenn, please go ahead.
Thank you, Sharon. Good day, everyone. Before I get going on the carbon capture landscape, maybe a few words about myself. I'm an engineer located in North America, in Canada, and I have a master's in finance, and my experience spans notably the natural resources, oil and gas, and energy and clean technology sectors. I started off in oil and gas exploration in North America, or worked throughout North America, moved on to develop natural gas storage, liquefied natural gas import into North America, and then went to the other end of the pipeline and worked on carbon capture. And then finally, the development of high purity alumina for EV batteries. There are two aspects of my background that directly touch what we'll be discussing here today with Dotz. One is, in my oil and gas background, one of my first responsibilities in Western Canada was to drill CO2 injection wells 40 years ago. Now, these wells weren't used to sequester CO2, as we will be doing in the next decades, but they were used for enhanced oil recovery. But that ties into what we will be doing with the CO2 that will be captured. The second part of my experience is in carbon capture. I led a company that took a technology from university into the lab, scaled up to a lab pilot, an industrial pilot, then a commercial demo at 30 tons per day, and that commercial unit is still operating today. So this morning, I'll touch upon three aspects of carbon capture. First, why must we capture carbon moving forward? Second, from what sources? Where should we be concentrating our efforts? And third, what is driving the economics of capture? What is making it financially viable? So on the first point, excuse me, why must we capture carbon? Well, the fundamental issue is, over the last decades, we've been pumping a lot of CO2 into the air. We're presently at about 420 parts per million of CO2 in our atmosphere, and this has caused a direct correlation to global warming or an increase in temperature. Our average surface temperatures since the early 1900s have increased on average about 1.2 degrees centigrade. And I'll be coming back to that number in a few slides. Net result of all of this, noticeable impacts in our weather patterns, a heating climate, and heading towards what some may call a climate crisis if we don't do anything about this. So what are the culprits leading to this? What are our biggest emitters of CO2? Simple answer, straightforward answer, where I started my career: fossil fuels, notably coal, oil, natural gas, in that order, added to cement. Cement production, by its inherent process, emits a lot of CO2. So we have fixed sources or point sources of emissions in the world, and then transportation or non-fixed sources. But of the 36 billion tons per year that we emit, or the 36 gigatons per year, 60% of global emissions, or 24 gigatons, come from the power industry and industrial processes. And I must note, though we are embarked on heading to net zero or to use of cleaner technologies, our present use of fossil fuels are still growing. So where does carbon capture fit into all of this? I was just saying we're looking towards a net zero future. That goes by the use of cleaner fuels and cleaner energy. You think of wind, solar, geothermal, hydrogen, electric vehicles. But in all scenarios going forward, fossil fuels will remain a major source of energy. So to get to a net zero future or a lower CO2 future, the use of those fossil fuels and their emissions will have to be abated, i.e. the CO2 will have to be captured. So how big is that problem? How much CO2 will have to be captured and sequestered? Well, recall that I talked about the average increase in global temperatures. We're presently at about 1.2 degrees centigrade, and the International Energy Agency and all of our governments have agreed that to have a livable climate going forward, we must limit that rise to 1.5 or a maximum of 2 degrees centigrade. So under that scenario, how much CO2 will have to be captured? Well, they estimate, the International Energy Agency, that from now till 2030, which is 7 years or less than 7 years, we will have to be capturing 1.2 billion tons of CO2 per year, mostly from coal, natural gas, oil, and industry. By 2050, we'll have to be capturing 5.6 billion tons of CO2 per year. Sounds like a big task. Where are we today? We have 40 million tons of capture operating today. So our capture capacity on a global scale must grow by a factor of 150 times. So we're already behind the curve. Fossil fuel growth is still growing. So the task at hand is quite important. So why should anyone capture CO2 other than the negative environmental impacts? What are the economic drivers of doing it? Well, until recently, there was no important cost to emit or no value related to a ton of carbon. Well, this has changed quite dramatically over the last 5 to 7 years. So a value of carbon or a ton of carbon is now valued through two pricing mechanisms, either an emissions trading systems or the ETS, which is the cap and trade market, notably found in Europe, or through carbon taxes, which is a direct tax on emissions. Presently, more than 25% of global emissions are covered by pricing mechanisms. Now add a third mechanism to that, which is more the carrot than the stick, and I'm talking about the US approach here, where they have put into place refundable tax credits for capturing your CO2. So when we add the ETS, the taxes, and the US tax credits, over 40% of global emissions are presently covered by a pricing mechanism, which is driving adoption of capture technologies. So what are some of these prices or some of these values that we're seeing, and how have they evolved over time? Well, if we focus on North America at first, in Canada, the carbon tax is presently $60 a ton, growing to $120 in 2030. The US tax credit is at $85 a ton, so both in the same range. And looking over to Europe, which is a market-driven approach, we see that the value or the cost of emitting is between $80 and $100 a ton and rising. So the value or the cost of carbon is increasing, and it's driving the financial viability for the emitters to adopt or implement carbon capture technologies such as ours. Add to that governments are allocating billions of dollars for upstream or front-end carbon research, development, and demonstration, and also supporting the emitters by giving them incentives to invest and capture their emissions. So as I was just saying, some sample of examples of the government push or the governmental push on a global scale of carbon capture technology. You've heard of the Inflation Reduction Act in the US. Well, over $2 billion has been allocated to cut carbon pollution in the US. The European Union, on top of the $100 credits or cost of credits, has allocated more than $3 billion for funding of specifically funding carbon capture and sequestration projects. And even in your area in Australia, the government has announced some major investment to push forward clean energy and management and abatement of CO2. So how big is this market? What does it represent for a technology developer and a technology user? Go back a couple slides. some numbers. 6 billion tons of CO2 must be captured from now to 2050. Of the value of a ton of CO2 is about $100 today in 2023. So that gives an addressable market going forward of about $600 billion per year in 2023 dollars. This fits well with the estimates of the US Office of Clean Energy, where they estimate $100 billion addressable market size in 2030 in the US alone, and 600 billion in 2050. Then again, just in the United States. So, in summary, I think we must, and it's clear that we must capture our CO2 to reach climate goals. A totally clean energy future is not there and not for the foreseeable future. So we must abate and must capture the emissions from our uses going forward of fossil fuels. The task is huge. We must capture 6 billion tons per year. Recall, we're capturing 40 million right now. So we must increase that 150-fold from now to 2050. For the first time in a long time, the value or the cost or the value of a ton of carbon or the cost to an emitter is strong and it's growing. Add to that government subsidies for both the emitters and the technology developers, and we have a very, very strong push on technology adoption and technology implementation. Thank you all, and thank you, Sharon. Back to you.
Thank you, Glenn, for this educative overview. Now, it is my pleasure to introduce our next speaker, Yasmina Kafka from Syntef Industry, who will provide an overview of the carbon capture technologies and a little focus on the solid solvents. Yasmina, please go ahead.
Thank you, Sharon. Good day, everyone. As said, the topic of today's talk is carbon capture technologies and a little bit information about the materials that are used in these processes. But prior to that, I would like to introduce myself. I work as a research manager at one of the Scandinavia's largest research institutes called Syntef. My background is in chemistry, more specifically materials chemistry from the University of Oslo, where I have studied porous materials called metal-organic frameworks for the applications in separation, mainly carbon capture and catalysis. My main research interests are within green technologies enabling emission reductions, enhanced energy and resource efficiency, but also in general, everything that deals with a green transition. And this is also where the research group that I'm heading has its main research interests. Now let's go over to the more scientific part. Glenn has already presented quite well the problem we have with climate changes, which are caused by the increase in the CO2 emissions. So in order to find solution for that, we have to map what are the carbon capture processes, where do we have the largest emissions, and where do we place a potential CO2 capture technology. So in this slide here, you see an overview of the different carbon capture processes. The first line is something that we call post-combustion, which is related to the production of the power and heat, where you put some kind of fossil fuel, you burn it in air, and you emit large amounts of CO2. But the good thing with this one is that the CO2 is emitted at the end of the process so that you can retrofit a potential CO2 capture technology to the existing plant. In the next one, which is called pre-combustion, you start with the solid fossil fuel that you first convert into a gas mixture containing both hydrocarbons, hydrogen, and CO2. But before this mixture can be used to produce power and heat, the CO2 has to be removed. And that means also that the technology that's applied has to be applied somewhere in the middle of the process, which again implies that we cannot retrofit CCS technologies to this carbon capture process. We have to start with the newly built plants. Then we have something which is called oxy-fuel production, oxy-fuel power and heat production, where instead of burning fossil fuels in air, you do that in pure oxygen, and by that you produce higher concentration of CO2 in your off-gas. But the technologies that can be applied here are more or less the same as for the first line, called post-combustion. And then to the last line, which represents the industrial processes, a general presentation of, let's say, main emitters like the cement, steel, ammonia production, where the CO2 is emitted from their final off-gases. And again, we have a possibility for retrofitting a CO2 capture technology. And this is where we will also place our focus in the remaining talk. And the adsorbents that I will be talking about are also the ones that can be applied in these 3 lines. Next, please. So what are the main technologies used to capture CO2? We have 4 categories: absorption, membranes, cryogenic separation, and adsorption. And in the end, we have something that is called hybrid processes, which are actually just various combinations of the 4 other technologies. So I will now go through each one of them and give you a brief introduction of every of them. Next, please. But before I do that, I would like to present some important parameters that have to be considered before we select our CCS technologies. And this is quite important so that we know what technology to apply to what emission source, because there is a range of different technologies that we can select from. So we have to start by taking, what is the CO2 content in the flue gas? Are there any impurities there that has to be removed before we capture the CO2? We have to put a target for the capture rate, meaning how many percentages of the CO2 from the off-gas has to be removed. What is the purity of the final CO2? What is the target? What are the requirements? What is the energy consumption of the different processes? And does the energy has to be supplied in the terms of heat or electricity? And then in addition to this, we need to think of what is the footprint of the technology that we want to install. Are we creating additional emissions and waste that are influencing the environment in a negative way? How easy is the technology to operate? What is the investment cost? And how easy is it to scale the capture process? So all these parameters has to be considered before we make a final decision. So I'll now go through all these 4 main categories of CO2 capture technologies. The first one is called absorption. This is the most mature technology, and it is based on the aqueous solvents, where the solvent is falling through the left column in the picture there, while you have your off-gas coming from below. And when these 2 come in contact with each other, the CO2 is absorbed in the solvent. The solvent is then accumulated in the bottom of the column, and it is saturated with the CO2. This solvent is then moved to the next column, which is called the regeneration column, or the stripper, where the CO2 is removed. And this is normally done by just heating this aqueous solvent mixture. The heat releases the CO2, but what happens also is that the heat can cause the decomposition of your solvent. And by that you then generate additional emissions, which could have a really negative impact on the environment. In addition to that, you can also have problems with the corrosion, depending on the type of the solvent that you're using in your process. But the good thing with this one is that you capture most of the CO2 from your off-gas. You can achieve capture rates higher than 98%. And the CO2 stream has a really high purity, almost 100%. But as said, it has also quite some drawbacks. So I don't know if one should go into this direction if one wants to capture all the CO2 emissions. We have to consider the alternatives as well. So next, please. Then we have membranes. This technology is appealing because it is operationally simple. You don't use any additional chemicals. You have a membrane, and on one side you have your off-gas, which is then pressurized so that you have a driving force to your membrane. But the material that is used to make the membrane itself is only permits certain molecules to pass through, like in this case CO2, and it's also only selective to CO2. When I say only, it's just partly true because some other molecules also gets through the membrane. But this is the driving mechanism. This is an electrically driven process. The challenges here is the technology is not that mature, and there are not that many membranes on the market that can actually be applied for this. So you don't have such a big variety of materials that you can select from. In addition to that, the material has to be tested with representative flue gases, not just the model compounds. So still some way to go to commercialize these processes as well. Then we have something which is called cryogenic separation. What happens here is that you just cool down your flue gas to a point where the CO2 is condensed from the gas phase to the liquid phase, and through this mechanism you separate CO2 from your off gas. But the challenge is that the majority of the emissions contains large amounts of water, which means that this water has to be removed prior to the condensation of the CO2. So you have a process which is highly expensive because first you have to remove all the water and then condense the CO2. So one is the price, the other is that this process has not been studied that much, not for the CCS. There's very little data out there that we can rely on. And it's also a question if there are enough developers that can deliver equipment so that this technology can be scaled up. But there are variations of that technology and others in combinations. And then the absorption technology, the last but not least, is the one that my group has been working a lot with. This is a process that is based on absorption of CO on a solid state material. And the material normally has to be transformed either into some kind of particles or monoliths before this can happen. And another thing here is that we have a large variety of solid sorbent materials that can be applied in this process. And in addition to that, we can have a large range of process configuration. Your material can be put in either as a fixed bed, fluidized bed, or a moving bed. And with all these parameters that you can vary, you have a quite large opportunities for the development and optimization of the CCS technologies. The main challenge with this one is the heat integration, because you don't have such a good contact as you have between your contactors and the solid as you have in the liquid phase. But you have the benefit of the large potential for the development and also lower energy consumption than in, for instance, solvent-based technologies. These technologies are not as mature as the solvents, but they have been demonstrated at the commercial scale. Next, please. Yes. This is just a summary of the different technologies, so I think we can skip this one. Yes. Now over to the solid sorbents that are used in the adsorption-based technologies. There are various families of CO2 sorbents, and we normally share them in two main categories. One is which we call low temperature sorbents, and then we have a high temperature sorbents. But the low temperature sorbents are those that are applicable for the processes that I just mentioned and for the green lines that I indicated in one of my first slides, the post-combustion processes, meaning the processes that are suitable for retrofitting the CCS technology. So that's why I will talk about low temperature sorbents. Next, please. Here we have some of the main low temperature sorbents. On the left-hand side, you see those that are commercially available and quite established materials in the market. You have activated carbons that are easily readily available, easy to make, stable materials. Then you have zeolites that are also commercially available materials, often applied in different industries, particularly in catalysis. You have silicas that are also easy to make and and readily available, and all of these can be amine functionalized to improve their properties for the application within CCS. And then on the right-hand side, you have a younger, call it kind of porous materials that can be applied in the CCS, which is called metal organic framework, where materials are made out of metal oxide clusters combined with different organic linkers. And you can use almost any metal from the periodic table of elements and a large number of the organic linkers, which then opens up great possibilities for designing new structures that can be custom made for the application. But the challenge here is often that these materials are not stable enough and cannot be scaled up for these applications. So next one, please. So which material do you select for your application? Because you have a large range of materials that you can select from. So what determines their applicability? We have something that is called absorption isotherm. That's the curve that you see on the right-hand side. This is where you see how your CO2 uptake in the material varies as a function of the pressure. And this helps you determine what are the optimal operating conditions for the material that you have selected. So you need this kind of data. But in addition to that, you need to have material which is highly selective to CO2, meaning that you have a good affinity only for CO2, but not for the remaining molecules, so that you can make pure CO2 streams. Your material should be physically stable so that you can have it in the process for a long time before you have to change. And you should also have quite good adsorption kinetics. And with this, I mean that your CO2 should be able to absorb and desorb from your material quite fast so that you can have an efficient process. You can run fast, more efficiently. And then in addition, the materials should be easily scalable because we would need tons and tons of these materials in order to apply them in commercial scale. And please just go back once more. Yes, for the MOFs, you can design materials that can have a perfect selectivity or really high capture capacity, but you will miss on the physical stability or the adsorption kinetics, for example, or the material scalability. And that would exclude these materials from, I would say, commercial applications, at least in the near future. And that's why we have to focus on the more established materials that can be made in large scale and that are stable enough, even though they might have somewhat lower adsorption capacity. And in there, I see activated carbons as one of the best candidates. Some selected zeolites, not many of them, and silicas. But these are the three categories, with activated carbons being one of the main ones for the future application in CCS. So with that, thank you very much for your attention.
Thank you, Yasmina, for sharing with us from your experience. And now I would like to introduce our next speaker, Professor Tor from Rice University, who will provide an overview of the innovative technology converting plastic waste into a carbon-based solid sorbent for carbon capturing. Since Professor Tor is based in Houston, Texas, he cannot attend in person given the time differences and provide us with a recorded presentation. Before I will start the video, I would like to provide some background about Professor Tor. So Professor Tor is a professor of chemistry, computer science, and material science and nanoengineering with over 30 years of experience at University of Rice. Dr. Tor have over 650 research publications and over 200 patents, and dozens of successful technology commercialization get out of his lab, including some of them that you are well familiar in Australia, like Weebit and Dotz. Dr. Tor was listed in the world's most influential scientist mind and in other publications, and we are happy to have Professor Tu as part of our company as a scientific advisor in our advisory board and as a co-founder of Dotz. And with that intro, I would like to introduce this video.
Hello, my name is James Tour, and this is going to be a presentation of some of the technology that we've developed in our laboratory. And this was the genesis of some of the work that Dotz is now working on. So let me share with you from the academic perspective some of the work that we've been doing. This is going to be CO2 capture on plastic waste. And plastic waste is a big problem in the world, as many of you have probably come to realize. And there's 275 million tons of plastic waste is generated every year. And so it's a big problem that needs to really be dealt with. Along with that is we have found that while many times plastic waste can be pyrolyzed, and it can go into small molecules and then circled around and made into new polymers. What we have found is that in this, if we add a compound like potassium acetate, we can actually get this CO2 sorbent to form a carbon material, and we can use this carbon material to trap carbon dioxide. And so 60% of all CO2 emissions are from large stationary emission points. So they're not coming out of the back of a car, which is moving around. They're from stationary emission points. And so this is what we're going after. This is the type of work that we're trying to do, is to say, can we make a system that could trap CO2 from flue gas? So for example, you'd have a power generation unit, and it would have the flue gas would be captured, and we capture the CO2 from that flue gas. That is the area that we're trying to look at here. Now, what's done today is liquid amine towers are currently used in industry for post-combustion CO2, where you take an amine, you trap it with CO2, and so it takes two amines to get one molecule of CO2, and then you regenerate it by heating it to 120 to 140 degrees. Keep that temperature in mind. It's energy intensive, you get solvent degradation, and there's a lot of corrosivity with the amines. But it has high CO2 selectivity, and it can absorb carbon dioxide at 1 atmosphere pressure. What we are going toward is solid sorbents. There are other solid sorbents on the market. There's something called MOFs, metal organic frameworks. Those have good CO2 capacity, good selectivity, but they're not water resistant. Generally, they're not water resistant, and generally they're expensive. There's other zeolites you can use, but often they can have good capacity, good selectivity, but the regeneration cost is high. We're going toward porous carbons, where the CO2, they have high CO2 capacity, selectivity, they're resistant to impurities, and they're inexpensive. That's what we'd like to look at in what we're making. And there's another process that's out there for taking waste plastic, and you can heat it up in the presence of zeolites, and you can generate fuels, waxes, monomers, and ash. The difference that we're doing is that we are doing the same sort of thing, but we're adding a few other compounds to it. And what happens is, in addition to making paraffins, linear alpha olefins, and other building blocks, as well as a porous carbon on which you can trap CO2. So we're taking a waste product, waste plastic, and using it to trap CO2 while making other things out of the plastic. And that's going to really help in thinking about this process. So this is high density HDPE, high density polyethylene derived systems. We can generate it with a high surface area. So if we're adding 4:1 high density polyethylene, 4 parts of a potassium acetate to high density polyethylene, heat it to 700 degrees, we can get a material that has a surface area of almost 1,300 meters squared per gram. The key here is it has many of its pores, most of its pores are less than 1 nanometer in size. That's going to be really important for trapping CO2. because CO2 is less than 1 nanometer in size. And so this allows the formation of a carbon material that can trap carbon dioxide. And so this is what it looks like. It is highly porous, but these are big pores. It is within these big pores that you have much smaller pores that are going to be trapping the CO2. And so this high density polyethylene derived sorbent has high CO2 uptake. So you see it at very low pressures. This is the pressure in bar or atmospheres, the same thing. It rapidly absorbs CO2. And flue gas is generally at 1 atmosphere of pressure. And so you have to be able, so this is that bottom part just expanded. And you can see that at 1 atmosphere, you have about 15 or 16% uptake is what we were getting on the CO2. And this is using this 4-to-1 and heating it to about 600 to 700 degrees. So taking potassium acetate and high density polyethylene, we could activate it and we could pick it up, and 4-to-1 was our best temperature to do this at. And then we were activating it at about 600 to 700 degrees. And we can get this high uptake material, which is almost up to 18% by weight CO2 capture. And then what happens is also that we studied very carefully the temperature at which we activate this. And if we activate it at 700, it's actually best. So you can get the highest percent uptake at 700 degree activation as we make this material. Our sorbent process is green and safe in that we don't exceed 700. As long as we stay below 750, we don't generate potassium metal, which then would make it a more dangerous process. So we stay below that, and you can look at where our work is compared to a lot of other work in the activation temperature that they need. We can do it at 600, we can go up to 700, but we're below where most people are heating their material. And here's the CO2 uptake in a flowing system, because this is what we're going to be having. And you see that argon and nitrogen are not retained by this sorbent, where CO2 is retained. That's what you want. You want CO2 retained. You want inert gases, particularly nitrogen, which is what most of flue gas consists of, nitrogen. You don't want that retained. And you can see the difference between the uptake of CO2 versus the uptake of nitrogen. And this is very important, that you have a good selectivity of CO2 over nitrogen, and that's what we've got. And now you can see that we can even do this under real flue gas type conditions where we have added water in there. So you always have, when you have a flue gas, you have CO2 coming out, you also have water. And so adding water to this does not inhibit the capture of the CO2. So this is under more realistic flue gas conditions. Now the sorbent can be regenerated. We can regenerate this sorbent at about 75 degrees. If you remember, the aqueous amine towers need 120 to 140 degrees. 75 degrees can be even just excess industrial heat from other processes. Once you get up over 100 degrees like that, then you have to use superheated steam. And that's going to be so this can be generated much more easily without as much energy in the regeneration. And the pickup is very fast. It's kinetically traps the CO2 very, very quickly. Kinetically traps the CO2 very quickly. The other part about this process is that the plastics wastes, in addition to forming this material that can adsorb CO2, we're generating a lot of other byproducts that have high value. These are alpha olefins. This is what we detect in our system, these alpha olefins. And when we look at this, these are hydrocarbon species that are alpha olefins. And so if you look at the price of these, you can sell these alpha olefins. And so you're generating a product that you can also sell, which can make up for the cost of even making this material. So you can see that all the different products that you can generate through that. And Saudi Aramco actually helped us to crunch some of these numbers with my student Wala Alghozi, who worked for Saudi Aramco, and then she came here as a graduate student for 4 years and then went back. And if you look at the cost of the raw materials, it turns out that if we sell the materials on the US market, there can be even a net profit just from the waste materials that we generate, particularly the alpha olefins. that come off. So this is a way to even do this in a way to make money, to make the material. And then it works with all different types of plastic, as well as with textile and construction plastics. Half of all plastic waste is not the type of things that you and I normally think about. It's from construction plastics and textile plastics, things that cannot easily be recycled. You can't recycle these because a lot of these are thermosets and not thermoplastics, but this even works with these systems. And so in conclusion, we've come up with this system where I think that we could possibly make money making the material and then make money using the material to trap CO2. So we're taking waste plastic, which is a real problem, making a material that can capture CO2, and then make other compounds that we can sell into the chemical industry. And with that, I'm going to end and conclude and stop the recording. Okay, thank you. Hello.
Now, it is my pleasure to introduce our last speaker for today, Dotz founder and CTO, Dr. Michael Stein, who will provide an overview of Dotz Earth Development Plan. Michael, please go ahead.
Thanks, Sharon, and good afternoon, everyone. My name is Michael, and I'm the CTO and co-founder of Dotz Nano. My background is a PhD in nanotechnology, together with a master's in chemical engineering and an MBA. I have over 15 years of managerial and research and development experience focused on commercializing academic concepts to products. Next slide, please. So, as you may know, technology can be categorized based on technology readiness level, or TRL, while all CO2 capture technologies also face the obstacle of being capital and energy intensive. In the following graph, we compare different technologies, CO2 capture technologies. You can see that the x-axis is the technology readiness level, and the y-axis is their cost effectiveness. As you can see, while solvent technologies are the most mature one, and Yasmina mentioned that, and many of them at the demonstration stage. However, the improvement in these well-studied technologies are very limited and typically focused on marginal enhancements of the chemistry or the engineering design of the CO2 capture unit. On the other hand, the solid sorbents pose a significant room for improvement and increase in the cost effectiveness of those CO2 capture systems, but unfortunately, most of them at very TRL level. Specifically, the solid-based sorbent technologies were reported to have lower regeneration requirement, better absorption capacity, better selectivity, and we believe that as a result of this, they have an enhanced cost effectiveness. That's why at Dotz we believe that in the future the solid-based sorbent technology will substitute the solid-based ones. Next slide, please. So at Dotz, we do believe that the technology that we license is the future of the industrial carbon capture, since it simultaneously addresses two of the most acute environmental challenges. First of all, the plastic pollution, and that's a source of our process, and carbon sequestration. It represents the next evolution in the carbon capture technology, offering an efficient and sustainable approach to drive industrial decarbonization. We believe that we have a differentiated technology with clear benefits that can make a real impact. The technology provides a renewable, simple process from waste plastic. The sorbent have a high absorption capacity due to unique structure and large surface area. It has high selectivity. It is regenerable and compatible with diverse CO2 sources. Next slide. Dotz, we did generate a clear development roadmap to advance our technology through commercial development with multiple value creation milestones. And we set the following development objectives. The first one is the optimization and the scale up of the sorbent process. from the milligram scale that we licensed from Rice University to the kilogram quantities, and we're doing that as we speak. This will be followed by design and development of the bench scale unit, or BSU. This stage will enable us to demonstrate the technology capabilities and validate its techno-economical parameters toward an industrial pilot. And ultimately, we are aiming toward the design and construction of large industrial pilots. And I will briefly present its conceptual design in my next slides. Specifically regarding the timelines, we do plan to optimize our sorbent and meet the goals of BSU within the next 9 to 12 months, and we will leverage the Syntef collaboration and extensive experience to expedite that. Next slide, please. So we are planning to design and implement a simple, straightforward, and modular process, which will be based on several parallel columns. These columns will be packed with Dotz solid sorbents, and these columns will continuously capture carbon dioxide from a point source emitter. Typical CO2 capturing process will be based on the following steps. In the first stage, the CO2-rich flue gas from a point emitter will enter the Dotz capturing process. Our sorbent in the first capture column will selectively separate the CO2 from the flue gas. The CO2 will be absorbed in the pores of the carbon based on sorbent through physical bonds, and then a CO2 lean flue gas will release into the atmosphere. Once a carbon-based sorbent will be saturated, it can be regenerated. During this regeneration process, the CO2-rich feed gas will be diverted to another parallel column for continuous removal process. During the regeneration, vacuum or heat will be used to release this captured CO2 and regenerate the sorbent. The released pure stream of CO2 will be compressed and liquidized, and then transported via pipeline to be safely stored or used. We do plan to expedite our research and development efforts by establishing strategic development collaborations. And as the first step toward that goal, we recently partnered with Syntef, one of Europe's largest independent contract research organizations. This collaboration will allow us to advance and optimize our Dotz Earth technology, leveraging Syntef's extensive experience in carbon capture and storage sector. And we believe that with collaboration with Rice University and Syntef, we do have a superior development team that can advance Dotz development program toward achieving our goals. Our initial focus, like I mentioned, will be to advance the development program to the bench scale unit, technology optimization, and scale up. Next slide, please. So to conclude, we do believe that solid sorbents, and particular carbon-based sorbents, is a game changer for the carbon capture industry. Once developed, this technology can provide emitters and energy efficient and environmentally friendly carbon capture solution. And the combination of its high absorption capacity, its selectivity, and expected low cost of ownership will make it ideal for industrial point source carbon capture. And thank you. And back to you, Sharon.
Thank you very much, Michael, for providing us more color regarding the development plan of Dotz Earth. And now I would like to open the session for the Q&A. I got during this presentation some questions from the attendees, and I will read some questions we received from investors during this presentation and will turn it to the relevant speaker. So I'll start with the first question that we got, which is, what does industrial decarbonization involve? And I want to refer this question to Glenn, please.
Thank you, Sharon. There are two paths to industrial decarbonization. One is using cleaner fuels, for example, hydrogen, which does not emit CO2 upon combustion, using other sources of energy when you can use that energy, so wind, solar, or others. So that's part of the answer. The part that interests us and that is an important part of industrial decarbonization is capturing the emissions of the fuels and the energies that we will still require going forward. And those are fossil fuels in one case, and also our most important building material, which is cement, which naturally releases CO2 during the cement production process. There are no two ways around it. So industrial decarbonization is one, cleaner fuels, part of the answer, but two, capturing our emissions and storing those emissions over geological time, getting rid of them underground.
Thank you, Glenn. The next question we got is, what makes solid sorbents technologies an alternative to the current amine-based technologies? And I think, giving the presentation, Yasmina is the right person to direct this question to. Please, Yasmina.
Thank you. The amine technologies are, as said, the most mature ones, and they have actually progressed quite a lot, as Michael showed in his slide. They have the highest zero level. But the challenges with them are, one is that they are highly energy intensive. You have to use a lot of energy to run this process. If you apply amine-based technology on a power plant, you would reduce your power output by 20 to 40%. And this can be significantly lower if you move over to a carbon, or call it sorbent-based technology. So that's why we are looking for alternatives. One is the energy intensity, but the other one is also, which is quite important, we are trying to solve one environmental problem while not creating another one. And with solvents, you are actually doing that because you have emissions of the solvent that has decomposed during the process. And this is what you want to actually, you want to stop emissions. You don't want to generate new ones. While for the sorbent-based processes, you don't have any chemicals than the materials itself, where you have adsorption and desorption of the CO2. So that's why this is a potentially viable route to decarbonize the industry.
Thank you, Yasmina, for the clarification. The next question was, what should we expect as investors looking forward? How can we track your progress? And I'd like to turn this call to Michael to share with you the development plan and what should we expect as part of the development roadmap. Please, Michael.
Sure. So like I presented, we have a clear roadmap in front of us with key value creation milestones. And what we're planning to show in the near future and achieve is several significant milestones, including the scale up of our process. So we license the technology. This is very early TRL level. It's at milligram scale. We are completing the technology transfer to our labs in Israel. That will be followed by scale up, which also a very significant step. And we believe that we'll be able to achieve it within the next few months to a few quarters, basically scaling the technology from milligram quantities to kilogram quantities. That, of course, all of that will be followed by patent applications, and we're already writing new patents regarding this technology. And every scale up, the bench scale unit that we plan to design and manufacturing during the next 12 months, I believe is also a very significant value creation milestones. So yeah, back to Sharon.
Thank you very much, Michael. And if I may add to Michael's response, so in addition to the clear development roadmap, we do understand that there are multiple value creation milestones throughout the development roadmap. And the best way to understand it is just to benchmark to other companies, public companies that are active in this space, and just look at their market cap when they reach the pilot lab scale unit, and this is why we are so focused to get the next milestones of a bench scale unit followed by the pilot unit. In addition, we will continue to update investors while we're pursuing funding programs as well as strategic partnership, and as moment we have something to update, we will keep you updated. The next question is how you plan to fund your development programs, and I will address this question. Our main focus regarding the funding are the two main sources. The first one is the non-dilutive funding. There are, as mentioned by Glenn, a lot of development grants and government development programs that we will keep pursuing and applying for. Those budgets and development programs worldwide are providing support and financing for the development stage of such technologies, and this is the first priority for Dotz to secure. The second source, of course, will be the strategic partnership, where we believe once you secure a strategic partnership, so it is associated with upfront payment, milestone payment, and of course, co-development cost sharing. So those are the two main sources which will provide us with additional financing resources and flexibility to develop our Dotz Earth technology looking forward. And I think that this was the last question that I see in my list. And with that, I would like to move to thank, first of all, the speakers for taking the time and sharing their knowledge and experience with us. And let me take a moment to summarize the key takeaways that we heard today from these team speakers. First, we understand that all scenarios emphasize that in order to reach net zero, we must dramatically reduce CO2 emissions from industrial processes and energy production, which account for the majority of global emissions. The scale of opportunity in this space is significant. It is a multi-billion opportunity backed by increasing global pricing mechanism and government policies and budget mobilized towards development and adoption of decarbonization solutions. Solid sorbents have shown potential to address the main drawbacks of the traditional capture technologies, which are capital energy intensity and are paramount to drive capturing cost reduction. We believe that Dotz Earth as carbon-based solid sorbent can offer a cost-effective and environmentally friendly approach to drive industrial decarbonization. Developing of new technologies and collaborations across the CO2 value chain are the key drivers or the driving forces towards net zero. Technology innovators are one of the key enablers of energy transition, supporting industries and governments to find efficient solutions to mitigate emissions and to reduce industrial emissions. As a carbon management technology developer, our goal is to provide industrial emitters with a sustainable and affordable means to reduce their carbon footprint. Dotz is well positioned to achieve this goal, and we believe we have all the ingredients that will enable us to capitalize on this multi-billion market opportunity. And let me share with you those three main ingredients. First, an innovative carbon-based technology characterized already by SINTEF that can drive carbon capture cost reduction, and we look forward to advancing our breakthrough technology as a viable solution for industrial decarbonization. The second, we have the right team that can realistically hit the next stage. Highly experienced executive with proven track records, executing growth strategies in multiple tech companies. experienced scientist team with proven capability to take a technology from academy, to develop it, scale up it, and commercialize early stage technology. And we recently strengthened our board with the appointment of Glenn Kelly and Mitch Board, both climate technology industry experts who will provide a valuable insights as we position ourselves for the next stage of growth. And we have a clear strategy or strategic plan to make it happen, combining on one hand technologies and collaborations as the key driving forces. Establishing strategic partnership with leading partner is a key component in our strategy. While we constantly examining and identifying complementary carbon management opportunities to drive growth and enhance our carbon management technology portfolios. On the development collaboration front, we recently signed a strategic development collaboration with SINTEF to advance and optimize Dotz Earth, leveraging SINTEF experience in the carbon capture sector. This strategic collaboration is a significant step in advancing our breakthrough technology as a viable solution for industrial decarbonization. Beyond this, we have ongoing preliminary discussions with key players in high-emitting sectors to form strategic partnership that will allow us to develop and progress the development plan and test our solution in a real-world setting, providing our partners with a path to reduce carbon emissions. Before we close this event, I would like to update that I'm planning to arrive to Australia on mid-November and have meetings with investors and potential partners. If you would like to have a meeting with Dotz management, please, I encourage you to reach out our IR agency to coordinate. And with that, we conclude this webinar. I would like to thank everyone for joining us today. We look to continuing to executing on our strategy and to updating you on the next activity reports. Thank you very much all.